The rapid growth of video data has led to increasing costs for video transmission and storage. To address this, researchers have been exploring end-to-end neural video coding (NVC) to improve video compression performance. Existing NVC models can be classified into 4 categories: volume coding-based, conditional entropy modeling-based, implicit neural representation-based, and motion-compensated prediction-based. Inspired by the successes of large models in natural language processing and computer vision, this paper investigates the effectiveness of large models for NVC. A small baseline model, DCVCSDD, was used as a starting point, achieving higher compression performance than the reference software of H266 VVC under certain conditions. The authors analyzed the influence of model sizes on compression performance by scaling up the model sizes of the motion encoder-decoder, motion entropy model, contextual encoder-decoder, contextual entropy model, and temporal context mining module. The results show that increasing the model sizes brings significant improvements in video compression performance. The influence of model architectures on compression performance is also investigated by replacing the CNN architecture with mixed CNN transformer or transformer-only architecture. Based on these findings, a large neural video coding model, NVC-1B, with over 1 billion parameters is designed. Experimental results demonstrate that NVC-1B achieves state-of-the-art compression efficiency, outperforming the small baseline model. This work provides a foundation for future research in large models for NVC and anticipates that such models may bring video coding technologies to the next level. Key terms and concepts in this study include neural video coding, large models, motion coding, contextual coding, and temporal context mining. Technical equations and algorithms, such as the scaling law and the conditional coding architecture, are used to support the analysis and design of the large neural video coding model. Experimental results are presented, highlighting the significance of the findings and their implications for future research. The analysis and design of NVC-1B involved evaluating the impact of increasing the model sizes on compression performance and identifying the most effective architecture for large models. This research builds on existing studies, including the H266 VVC standard and the DCVCSDD model. By demonstrating the effectiveness of large models for NVC, this paper provides a new direction for video compression research. Experimental results are presented, showcasing the significant improvement in compression efficiency achieved by NVC-1B compared to the baseline model. A detailed analysis of the results is also provided, discussing the implications of these findings and future directions for research. This work demonstrates that large models have the potential to improve video compression performance, offering new possibilities for efficient video transmission and storage. In neural video coding, the impact of scaling up model sizes on video compression performance remains largely unexplored. To address this, we present a comprehensive analysis of the effects of increasing model sizes on video compression performance. Our contributions include scaling up different components of a neural video coding model, exploring various architectures, and proposing the first large neural video coding model, NVC-1B, with over 1 billion parameters. In the context of large language models and large vision models, scaling up has led to significant performance gains. For instance, GPT-3 and GPT-4 have demonstrated improved natural language understanding and generation capabilities, while Vision Transformer and its variants have shown enhanced performance across tasks. In contrast, existing neural video coding models have small model sizes, and the effectiveness of scaling up these models has received limited research attention. Our proposed NVC-1B model is designed to address this gap. We provide a framework overview of NVC-1B, followed by detailed analyses of the influence of model sizes and architectures on compression performance. Our results show that NVC-1B achieves significant video compression performance gains compared to smaller baseline models. We report on the compression performance of NVC-1B, providing insights into the potential benefits of scaling up neural video coding models. Our findings highlight the importance of exploring larger model sizes in neural video coding and demonstrate the potential for improved video compression performance through model scaling. This section of the research paper presents an overview of the proposed large neural video coding model, NVC-1B, which is based on the small baseline model DCVC-SDD. The framework consists of several key components: motion estimation, motion encoder-decoder, temporal context mining, contextual encoder-decoder, and entropy model. The motion estimation process utilizes the structure and detail decomposition-based method to estimate motion vectors between adjacent video frames. These motion vectors are then compressed and reconstructed using an autoencoder-based motion encoder-decoder. The compact latent representation of the motion vectors is quantized and converted into a bitstream using the arithmetic encoder. After receiving the transmitted bitstream, the arithmetic decoder reconstructs it back to the quantized latent representation, which is then decompressed by the motion decoder to obtain the reconstructed motion vectors. The temporal context mining module extracts multiscale features from a reference feature and uses multiscale motion vectors for feature-based motion compensation. This module also handles motion occlusion by employing a convulsed M-based long-term reference generator to accumulate historical information and learn a long-term reference feature. The long short-term fused temporal contexts are generated by fusing the long-term reference feature with the multiscale temporal contexts. The contextual encoder-decoder compresses and reconstructs the input frame, utilizing multiscale temporal contexts to reduce temporal redundancy. Quantization is applied to the compact latent representation of the contextual encoder, and the arithmetic encoder converts the quantized representation into a bitstream. The arithmetic decoder reconstructs the bitstream to the quantized representation, which is then decompressed by the contextual decoder to obtain the reconstructed frame. An intermediate feature from the contextual decoder is considered as the reference feature for encoding, decoding the next frame. The entropy model uses the factorized entropy model for hyperprior and the Laplace distribution to model the motion and contextual compact latent representations. The mean and scale of the Laplace distribution are estimated by combining the hyperprior, latent prior, and spatial prior generated by the quadtree partition-based spatial entropy model. For the contextual compact latent representation, a temporal prior learned from the smallest resolution temporal context is also introduced. The methodology section discusses the exploration of the influence of model size on compression performance. The model sizes of different parts of the small neural video coding model are gradually scaled up to understand their impact. In the realm of neural video coding, the relationship between model size and compression performance is a critical area of investigation. A recent study delves into this topic by examining the impact of scaling up the model size on 4 distinct components: motion encoder-decoder, motion entropy model, contextual encoder-decoder, and contextual entropy model. The analysis reveals that each component responds differently to model size increases. For instance, the motion encoder-decoder exhibits a slight performance gain with a moderate increase in model size, but further scaling up leads to diminished performance gains and unstable training processes. Conversely, scaling up the contextual encoder-decoder consistently improves compression performance without any observed instability in training. Similarly, the contextual entropy model also demonstrates sustained and stable performance gains as the model size increases. These findings underscore the importance of a balanced approach to scaling up various parts of the neural video coding model. By understanding how different components respond to model size increases, researchers can better design and optimize future models for optimal performance. This research contributes significantly to the field of neural video coding, shedding light on the intricate interplay between model size and compression performance. Neural video coding, NVC, performance is significantly influenced by model size and architecture. Scaling up the model size of key components, including the contextual encoder-decoder, contextual entropy model, and temporal context mining module, yields stable compression performance improvements. This is demonstrated through experiments that increase the model size, resulting in enhanced compression efficiency. In addition to scaling up model size, the authors investigate the impact of different architectures on NVC performance. Specifically, they explore the use of mixed CNN transformer and transformer architectures, finding that the insertion of SWIN transformer layers into these modules can further enhance compression efficiency. This is attributed to the ability of SWIN transformer layers to effectively capture spatial and temporal dependencies in video data. The results of these experiments are presented in figures 35, which illustrate the effectiveness of scaling up model sizes and adopting new architectures in improving compression performance. The findings suggest that increasing model size and incorporating SWIN transformer layers can lead to significant gains in compression efficiency, making them promising approaches for future NVC systems. Neural video coding models are explored, focusing on architectural designs and the impact of scaling up model sizes. A comparative analysis is conducted on models with convolutional neural network, CNN, mixed CNN transformer, and transformer architectures. Results show that CNN architectures generally outperform models with similar sizes in terms of compression performance. A closer examination of the transformer architecture's effectiveness in various coding modules reveals that while it can bring a small performance gain in the contextual encoder-decoder, its use in contextual entropy and temporal context mining modules leads to model instability and significant performance degradation. Based on these findings, a large neural video coding model, NVC-1B, is developed using a CNN architecture. To ensure stability during training, the allocation of model parameters is optimized, with a majority allocated to the contextual encoder-decoder, contextual entropy model, and temporal context mining module. The training process for NVC-1B involves multiple stages, each employing distinct loss functions. The optimization of model parameters and the use of specific loss functions at different training phases are critical to achieving stable and efficient model performance. The design of NVC-1B highlights the importance of carefully selecting architectural components and optimizing parameter allocation to achieve high-performance neural video coding. The NVC-1B model is a large neural video coding model designed to achieve high-quality video compression with low bitrate. To train the model, a periodically varying weight is used to control the trade-off between bitrate and distortion. This weight is incorporated into multiple loss functions, including LMED, LMERD, LRECD, LRECRD, LOL, and LOL-T, which are employed in different stages of the cascaded fine-tuning process. The model is trained on 7 frame videos from the Vimeo 90K dataset and tested on HEVC, UVG, and MCLJCV datasets in both RGB and YUV420 formats. The implementation utilizes PyTorch with the AtomW optimizer and a batch size of 32. Multi-frame cascaded fine-tuning is performed on 4 NVIDIA A800 PCIe GPUs for 28 days, leveraging forward recomputation backpropagation to alleviate CUDA memory pressure. In low-delay coding scenarios, the model is tested on 96 frames for each video sequence with an intraperiod of 32. The performance is compared to traditional video codecs, including HM16.20, VTM13.2, and ECM 5.0, with detailed commands provided for these benchmarks. By employing cascaded fine-tuning and a periodically varying weight, the NVC-1B model aims to reduce error propagation and optimize the trade-off between bitrate and distortion, controlled by the Lagrangian multiplier lambda. The performance of the proposed neural video coding model, NVC-1B, is evaluated using RGB-PSNR for RGB videos and compound YUV-PSNR for YUV420 videos, with a weight of 6:1, 1 for YUV components. Bits per pixel, BPP, and bitrate are employed to assess bitrate and compression performance, respectively. A negative bitrate indicates bitrate saving, while a positive value signifies bitrate increase. Experimental results for RGB videos are presented in Figure 7, illustrating rate distortion curves for the HEVC, UVG, and MCLJCV RGB video datasets. Reconstruction quality is measured by RGB-PSNR, demonstrating that NVC-1B significantly outperforms its small baseline model, DCV-CSDD. A detailed bitrate comparison in Table 3 reveals that NVC-1B achieves an average 25.1% bitrate reduction over VTM13.2 across all test datasets, surpassing the performance of DCV-CSDD, 12.7%, and state-of-the-art neural video coding models, including DCV-CDC, 18.3%, and DCV-CFM, 14.3%. The proposed model is compared to several benchmarks, including CANFVC, DCVC, DCVC-TCM, DCVC-HEM, DCVC-DC, DCVC-FM, and DCVC-SDD. The experimental setup involves input parameters such as input bit depth equals 8, frames to be encoded equals 96, source width equals width, source height equals height, intra-period equals 32, QP equals QP, and level equals 6.2. Results for YUV420 videos are presented in Figure 8, with corresponding bitrate comparison results listed in Table IV. The large model, NVC-1B, improves the average compression performance from 8.4% to 20.5%, outperforming ECM, 19.0%. These findings demonstrate the effectiveness of the proposed NVC-1B model in achieving significant bitrate savings while maintaining reconstruction quality. Page 9 of the research paper presents the evaluation results of the proposed NVC-1B model on various video datasets, including HEVC, UVG, and MCLJCV. Figure 8 displays the rate distortion curves of these datasets, measuring the reconstruction quality using YUV-PSNR. The results demonstrate that the NVC-1B model outperforms the baseline models, including VTM, ECM, HM, DCVC-DC, DCVC-FM, and DCVC-SDD, in terms of compression efficiency. Table IV presents a comparison of the bitrate % for YUV-PSNR, with VTM as the anchor. The results show that the NVC-1B model achieves an average bitrate of 20.5%, outperforming the baseline models. Notably, the performance gain on the HEVC Class E dataset is smaller due to the limited GPU CUDA memory, which restricts the number of frames used for multi-frame cascaded fine-tuning. Table V compares the average encoding and decoding times for a 1080p frame in seconds. The results show that the NVC-1B model has an encoding time of 4.44 seconds and a decoding time of 3.54 seconds, which is significantly faster than the ECM model but slower than the HM and DCVC-SDD models. The paper also presents subjective comparison results, visualizing the reconstructed frames of the NVC-1B model and its small baseline model, DCVC-SDD, in Figure 9. The results demonstrate that the NVC-1B model can retain more textures with a lower bitrate, achieving better subjective quality. The paper provides examples of the video SRC14 sequence, the racehorses sequence, and the Kimono 1 sequence, showcasing the superiority of the NVC-1B model in retaining sharper edges and reconstructing details. Finally, the paper discusses the limitations of the current implementation, including the restricted GPU CUDA memory, which affects the performance gain on the HEVC Class E dataset. Future work involves exploring the use of GPUs with larger CUDA memory to further improve the compression performance of the NVC-1B model. The comprehensive evaluation of the proposed large video coding model, NVC-1B, is presented in comparison to its small baseline model, DCVC-SDD. Figure 9 showcases the subjective quality comparison between the two models on various video sequences, demonstrating the superior performance of NVC-1B. The average contextual and motion channel bitrate distribution between the two models is compared in Figure 10, highlighting the differences in bitrate allocation. Notably, NVC-1B requires more encoding and decoding time than DCVC-SDD, as reported in Table V for 1080p video. However, its encoding time is significantly lower than that of traditional video codecs. Further optimization is expected through the development of lightweight techniques for large models. To understand the performance gain of NVC-1B, an analysis of the transform energy compaction is conducted. The contextual bitrate ratio, CR, of each channel is calculated using equation 7, which represents the average bitrate ratio of each channel of the contextual latent representation. The average contextual bitrate ratio is then calculated over all sequences, and the top 100 channels with the largest bitrate ratios are presented in Figure 10. The results show that NVC-1B achieves better transform energy compaction than DCVC-SDD, indicating that the proposed large model is more effective in capturing the contextual information in the video sequences. This analysis provides insight into the performance gain of NVC-1B and highlights the importance of transform energy compaction in video coding. The authors of the research paper compare the performance of their proposed large neural video coding model, NVC-1B, with its small baseline model, DCV-CSDD. They analyze the temporal contexts predicted by both models and find that NVC-1B generates contextual latent representations with higher transform energy compaction, resulting in a more concentrated bitrate distribution. This is beneficial for entropy coding. They also calculate the motion bitrate ratio of channel C for each video sequence, which indicates that NVC-1B can improve transform energy compaction for motion compression by end-to-end training. The motion channel bitrate distribution of NVC-1B is more concentrated, leading to higher compression performance. Furthermore, the authors analyze the temporal context mining accuracy and find that NVC-1B predicts smoother object edges with fewer artifacts compared to DCV-CSDD. This improves the temporal prediction accuracy and contributes to the performance gain of NVC-1B. In addition, the authors investigate the effect of scaling up the motion encoder-decoder on compression performance. They visualize the warp frames predicted by DCV-CSDD, M1, and M3 models and find that increasing the model size does not always lead to better performance. An inappropriate model size can reduce the accuracy of temporal prediction. Overall, the authors demonstrate the effectiveness of their proposed NVC-1B model in achieving significant video compression gains over its small baseline model. They conclude that scaling up the model size and optimizing the model architecture can lead to improved compression performance. Future work involves designing larger models with more efficient architectures to further improve video compression. In the realm of learned video compression, numerous research efforts have made significant contributions to this field. Key studies include the utilization of rate distortion autoencoders, 4, hierarchical encoding-based neural representation, 11, and conditional entropy coding, 16. The importance of scaling laws for neural language models, 41, is also discussed, highlighting their potential applications in video compression. Different approaches are analyzed, such as motion compensation, 38, spatial decomposition and temporal fusion, 32, and the utilization of transformers for image recognition at scale, 46. Learned contextual video compression, 34, plays a pivotal role in this field, along with the development of efficient temporal context learning, 37. These methodologies aim to enhance video compression efficiency by leveraging deep learning techniques. The text emphasizes the importance of understanding the trade-offs between rate, distortion, and computational complexity in video compression. It highlights how these factors are crucial for achieving optimal performance in various applications, from real-time streaming to archival storage. Moreover, the role of machine learning algorithms in optimizing video compression is explored. By learning from large datasets of videos, these algorithms can adapt to different content types and improve compression efficiency over time. In conclusion, the page provides a comprehensive overview of the current state of the art in learned video compression. It underscores the potential of deep learning techniques to revolutionize video compression and highlights the ongoing research efforts aimed at addressing the challenges in this field. This comprehensive list encapsulates the essence of a research paper, providing an in-depth analysis and technical refinement of its key concepts, methodologies, and findings. The study delves into various aspects of a complex topic, dissecting it into manageable parts for easier comprehension. The paper begins by introducing the subject matter, elucidating its significance in the field and its potential implications. It then delves into the methodologies employed, detailing the experimental design, data collection procedures, and statistical analyses used to draw conclusions. A pivotal section of the paper is dedicated to the presentation of results, where figures, tables, and graphs are utilized to illustrate the findings. These visual aids serve as a means to simplify complex datasets, allowing readers to quickly grasp the trends and patterns observed during the study. The discussion section of the paper provides an interpretation of these results, contextualizing them within the broader literature on the subject. Here, the authors highlight novel insights, significant discoveries, and areas for future exploration, emphasizing the potential impact of their research on the field. Limitations and assumptions inherent to the study are also addressed, underscoring the importance of considering these factors when interpreting the findings. This section serves as a reminder that scientific research is an ongoing process, with each study contributing to our collective understanding while simultaneously revealing new avenues for investigation. In conclusion, this paper offers a detailed examination of a multifaceted topic, employing a range of methodologies and presenting comprehensive results. Through its thorough analysis and thoughtful discussion, it contributes meaningfully to the existing body of knowledge, paving the way for further research and exploration in the field.